السلام عليكم ورحمة الله وبركاته. Share the presentation window. Okay, take it to the presentation mode. Okay, yeah, if you remember in our previous class, we discussed about the types of flow, where we explained the steady flow, uniform flow, unsteady flow. Here we considered the depth of flow as the guiding criteria for the flow classification. Okay, and have steady uniform flow, laboratory channel, unsteady, gradually varied flow, unsteady, rapidly varied flow when you have surges, okay, or flood wave, gradually varied flow. So now we will move to state of flow. Okay, we will move to state of flow, and here we'll look at Reynolds number. Okay, and then later we'll look at fluid number as well. Okay, so viscosity and gravity affect the state of flow in an open channel. Of course, this is obvious. Okay, the viscous force, which is exerted between the fluid molecules and the bottom, okay, and the boundary sides, okay, there is some friction that is being exerted as the fluid is flowing, okay, in form of viscous shear stress. Okay, and the shear stress, the viscous force is given by the shear stress multiplied by the area. Okay, and then you have gravity effect. As the fluid is flowing, you have the weight of the fluid. Okay, the weight of the fluid, which is as a result of the gravitational attraction. Okay, so all these affect the state of flow in open channel. So the Reynolds number and the fluid number are both relevant in the channel flow. Reynolds and Froude are all names of scientists, okay, that have worked, in this area and have contributed significantly. So that is why their numbers are used, okay, and these are called dimensionless numbers. So let me check what you are writing. I enabled your mic, so you can always talk if you want to, okay? Always talk. Let me see what chapter that we are taking right now. This is chapter 14. Okay, I'm done. Good morning. This is chapter 14. Okay, we started this last week. Okay, it is chapter 14. All right. Let me go back to the presentation mode. You're welcome. Although I made some slight changes, okay, so I will upload it after the class, okay, and then I will upload it after the class. I made some slight upgrade to the lecture, okay. So Reynolds number and the fluid number are both relevant in the channel flow. Okay, and Reynolds number is simply defined as the ratio. Like I said, these are called dimensionless numbers. Okay, we have them in fluid flow, we have them in mechanical engineering, you have them in aeronautical engineering. Okay, in fluid mechanics or water engineering, basically we have two. Okay, Reynolds number and fluid number are the most important ones. Okay, although you have others, like in the fluid mechanics, there is Weber's number, okay, and other non-dimensionless numbers. They are non-dimensionless because they are ratios of quantities with the same unit. Okay, if you have ratio of force to force, so the unit is going to cancel out. If you have ratio of quantities having the same unit, so are going to cancel. That's why we call them dimensionless numbers. Okay, dimensionless numbers. So Reynolds number is simply a ratio of the inertial force to the viscous force, and is expressed as follows for an open channel. Okay, the final form is VR over mho. V is the representative velocity or the average velocity of flow. R is what is called the characteristic length for open channel flow. Here, R will be equivalent to hydraulic radius, and you know hydraulic radius is the area over the weighted perimeter. Okay, this we indicated right from the beginning. Okay, those formulas. Yeah, the hydraulic radius is the area over the weighted perimeter. So R, if you remember, is area over P. P is the weighted perimeter. That is the perimeter, the boundary surface in contact with the fluid. Okay. And mho here is the kinematic viscosity. Okay. Which is mho is simply over rho, the dynamic viscosity over the density of the fluid, okay, which is giving us more, which is the kinematic viscosity, okay, while V is the average velocity of flow. Okay, it's even all presented here. Okay, so V is the mean velocity of flow, R hydraulic radius, V kinematic viscosity, which is equal to the dynamic viscosity over the mass density. Okay, so this is the simplification of the Reynolds number given by this formula here. Okay, so we said is the ratio of the inertial force to viscous force. What is this inertial force? What is this viscous force? I will explain in few slides to come. Okay, I'll explain. Although I explained the viscous force, of course, explain the viscous force, which is simply as a result of the shear stress. So the viscous force, by the shear stress times the area. Okay, and based on the Newton's law of viscosity from fluid mechanics, based on the Newton's law of viscosity, the shear stress is equal to mu and the velocity gradient. Okay, which you could represent as V over L. Okay, L is the characteristic length, which can vary from one problem to another, from one pipe, maybe are you considering pipe or open channel also? Like in this case, the characteristic length is R for open channel. Okay, for pipe, it can be diameter. Okay, so VL and the area here, the characteristic area, you can use L squared. Okay, for the area. So here you have this becoming mu V L. Okay, so sometimes we say that the viscous shear stress is proportional to this. Okay, because it's not all the time that the area is always equal to L squared. Okay, this is like a simplified form. Let's say when you have a square, that's when the area is equal to L squared. So we normally say that the viscous shear stress is proportional to this. It's proportional to this mu VL. Okay, and by now I already explained the viscous shear stress. Now the inertial force. What is the inertial force? The inertial force is simply going back up. Gentlemen, tell me, what is Newton's second law of motion? In statics, we are taught about the Newton's first law of motion, which is the basis for the equilibrium equations that you dealt with in statics. Okay, and then you dealt with the Newton's first law and Newton's third law. Okay, now what is the Newton's second law of motion? I want someone to state it. Tell me. Just talk. I enabled your mic already. What is the Newton's second law of motion? Like I always tell my students in statics, you cannot forget these laws, okay? You cannot forget the Newton's laws of motion, first, second, and third laws, because they are the basis. They form the foundation of engineering analysis, of most engineering analysis. When you're talking about civil engineering, mechanical engineering, these laws form the very foundation. Okay, so as a civil engineer, you cannot forget to explain these three laws, clearly at any point in time. It's not something that you just like memorize and forget about. No, at any given point in time, you should be able, when asked to state either Newton's first, second, or third law, you should be able to reproduce those laws and you should be able to explain them. I used to tell my students this even when hiring for assistant professor position, for professorial position, we ask candidates to state these laws. Just last week, we were recruiting, we were interviewing candidates for assistant professor position. I asked them to state Newton's third law of motion. So it's something that even if you finish, you graduate with your BS, get MS or PhD, even if you become full professor, you still can be asked to explain these laws at any point in time. Okay? So don't tell me that, no, I forgot it. So tell me, what is Newton's second law of motion? Oh, talk. I can hear you.
Second law, teacher, means when the mass, the force on an object is equal to mass.
What?
The force on an object is equal to the mass. That's what we have. F equal m multiply a acceleration.
But you say it's equal to mass, and now you are telling me about acceleration. Is that Hamdan?
Yes, teacher.
So F is equal to ma.
Yeah, sure.
Okay. Where is Bashar? Bashar, explain. Hamdan has given me the formula. The force on is equal to ma. So what is like the explanation? Bashar. Is Bashar around? Let me check. Muhammad Bashar. Okay, we're here. So go ahead. Any explanation that you can offer? Bashar, are you in the class or not? Muhammad Bashar, I saw you. You are present. So
I want to connect my phone.
okay, now tell me. I want you to explain the Newton's second law of motion.
Doctor, if the force acting like car on the other car, it will be earn the force by the proportion to its mass. I think.
What?
Like if you have two cars, it's like pushing together or push the other car. The
Okay.
force in it or the velocity, it will be, I think it will be earned to the other.
Okay, I will take my time to explain all these laws now, but I hope this will be the last time. I mean, you should be able to explain it in clear terms. Yeah, Hamdan gave me the formula F equal ma. Yeah, which is good, and Bashar tries to give me some explanation. Okay, so I will go back to these laws and explain them because all our derivation, this is what we are using. Okay, this is what we are using. Force analysis, civil engineering, mechanical engineering, these two you cannot do without understanding these concepts clearly, because all the derivation in fluid mechanics, in structural mechanics, in water, is all revolving around these laws. Okay?
Yeah, teacher, and when we deal with the motion equation, example, anything that depends on the second law of Newton.
Yeah, whenever we are dealing with force, even in the derivation that we did before, we are talking about forces acting, and then we sum these forces, and then we now equal to the rate of change of momentum. Even we did this before, but like I said, let me just go back slightly and explain these three laws, and then we move on. Okay, but like I told you, you should at any point in time be able to explain clearly. I'm telling you this because this is the time for you to incorporate it, to understand it in clear terms, because you can go and get your PhD and go for interview. I mean, we can ask you these dimensionless numbers. What is Reynolds number? Last week, I was interviewing someone. He has his PhD. He's a water engineer with a PhD. I asked him, what is Reynolds number? What is the ratio? What is the formula for Reynolds number? What is the ratio? Reynolds number is ratio of which force to which force, which is exactly what we are doing here. Do you get my point? These are basic concepts that no matter what, you should be able to remember them at any point in time. Okay? Whenever, I cannot remember how many times we ask candidates with PhDs to give us dimensionless numbers. I told you, we call them dimensionless numbers. Okay? Reynolds number, the fruit number, and mechanical they use Mach number, and chemical they also use Mach number and other dimensionless numbers. Is it clear?
Yes, clear, but what Reynolds number units, teacher?
Unit, it has no unit, it's dimensionless. That's why it's dimensionless. So it has no unit, because it's the ratio of forces. You have the inertial force over the viscous force. So force over force, Newton over Newton will cancel out. So it has no unit. So that's why it is called dimensionless. It has no dimension. Is it clear?
Clear, teacher.
Okay, so let me go back to the presentation mode like I promised, to just take you back on. All right. I said Newton's laws, they form the basis of most of the engineering disciplines. Okay. The first law is talking about, when you have forces acting on a body that is at rest, that is either at rest or moving with uniform velocity. Okay. So if you have forces acting on a body that is at rest, that body will continue to be at rest if the forces are balanced. Imagine yourself standing and you have two guys. This is you. And you have two guys, one pulling you this side. Let's say this is Hamdan pulling this guy, and this is Bashar pulling from the other side. Okay? If the forces are equal, let's say they all use 10 Newton. 10 Newton. They are equal but opposite in direction. Can you see that? So this man will remain in equilibrium, will not move. But if the force applied by Bashar, who may be stronger, I don't know, let's say Bashar apply 100 Newton, and then Hamdan apply 10 Newton. So here you have net force that is not zero. The net force here is 90, isn't it? So this guy will not be in equilibrium. He will be pushed towards Bashar, isn't it? But if the forces are balanced, he will remain in equilibrium. So what we are saying with the first law is that when you have a body will remain in its present state of rest if it is acted upon by balanced force. And by balanced force, it means that the vector sum of all the forces is equal to 0. Like when you take this is the x-axis, isn't it? If this is 10, this is 10, force is a vector quantity. This is plus, this is minus 10. So the vector sum plus 10 minus 10 will give you 0. So the vector sum of the forces is 0. Okay, and from there we now derive the equilibrium equations. And it will remain at rest if the vector sum of the forces is 0 and also the moment, because force create moment. The moment must also be equal to 0. So that's why you have summation F equals 0, and summation of all the vector sum of the moment be equal to 0. From the first one, you generate 3 scalar equations. From the second one, you generate 3 scalar equations, making 6, which we call the equilibrium equations. And these equations form the basis of statics. Statics revolve around all these 6 equations. That is it. Now, the second part of the third law says action and reaction are equal and opposite. When you have two bodies, you know, if a force acts on this body, okay, let's say this body is acting on this, okay, so this body will also exert equal but opposite reaction. It's like you sitting down on a chair, you exert your weight on the chair, the chair will exert equal but opposite reaction on you, which will be equal to the weight. What will happen if your weight exceeds the reaction? You will break the chair, because the weight and the action and action must be equal for equilibrium. So if you have your table, you exert weight on the table W, the reaction from the table must be equal to the weight. So R must be equal to W. If W is greater than the reaction, it will break the table. It will break it, because it has to be sustained. For equilibrium, they have to be equal. So action and reaction are equal and opposite. And here it is saying that force cannot act in isolation. Whenever you have a force acting, then you must have another force counteracting or opposing that force. So you don't have just, you know, as long as the body is in equilibrium. Now, coming to the second law of motion. When you have unbalanced force acting, in the first law it says when you have balanced force acting, okay, the body will continue to be at rest if the forces are balanced. Okay, and I explain balance in a simple way, like pulling in this direction and that direction, 10 Newton, 10 Newton. So that is a balanced force. What about if Bashar increases force to 50 Newton? The force is not balanced. You have resultant force that is not equal to 0 in this case. So this boy will move towards Bashar, meaning he will accelerate. His velocity will change. Initially, the initial velocity is 0. Now, he will have a velocity equal to some value. So the body will accelerate and will move towards the direction of the applied force. So the second law is now saying that when a body is acted upon by an unbalanced force, it will accelerate. And the acceleration is proportional to the applied force and acts in the direction of the applied force. Simple. So that is why you have F equal MA. Okay? That's why you have F equals MA. This is the resultant, you know, the sum of all the external forces applied, because they are unbalanced force. So this is sum of all the external forces applied. When applied to a body of mass M, the body will accelerate. Acceleration is simply change in velocity over time. Change in velocity over time. So the acceleration is proportional to the applied force and it acts in the direction of the applied force. So now you have mass. So it's simply F proportional to A. When you remove the constant of proportionality, you introduce a constant, which is the mass of the body. And that takes us to inertia again. Inertia is simply the tendency of body to remain in its current state. If you are sitting, if someone suddenly push you up, that is changing your velocity. You will be jerked back. That is inertia. If you are moving, let's say at uniform velocity, if someone suddenly stop you, you don't want to stop. It's like moving in a car and then someone is crossing the road and then you suddenly apply the brakes. If care is not taken, if you don't wear your seat belt, if there is a passenger, he can be, pushed off, through the windscreen, isn't it? That is because of the inertia. The mass doesn't, this is opposing change in velocity. Okay? So this gives the sum of all forces acting on this body M. And that's why we call it also inertial force. So this is the inertial force. This is the inertial force. F, the sum of all forces acting on a given mass. Okay? We call it the inertial force. And F equal ma, acceleration is simply what? V over t, change in velocity over change dv over t, isn't it? Okay, and then you have momentum, which is product of mass and velocity. Okay, so now you have, this is like, when you have m dv dt, this is rate of change of momentum. So the force is equal to the rate of change of momentum. Simple. And momentum is simply the mass multiplied by the velocity. This is just what you did in statics, okay? But like I told you, it forms the basis of civil engineering derivations. Most of them. Previously, we sum the forces all together. We will be summing the forces acting on a given fluid element. So that's why we'll be summing it, all the forces acting. Even now, we will go and derive, the energy equation, the specific energy equation. We'll do the same thing. We'll be summing all the forces acting. And the forces are basically, you look at the inertial force, you look at the gravity force, which is the weight, in form of the weight, isn't it? And then you look at the viscous force. From this one, so it's not from this one that we derive W equal mg. It is from the Newton's law of gravitation, okay? Although some are using this one, okay, because acceleration, this is when you have uniform acceleration due to gravity, you substitute A with G. But actually, W equal mg is derived using the Newton's law of gravitation, okay, which says that every two given masses attract each other with a force that is equal, that is proportional to the product of their masses and inversely proportional to the square of their distances apart. Okay, so in summary, I am still telling you what is the inertial force. This is the inertial force.
Teacher,
Constant force, the sum of all forces acting on a given mass, on a given particle, on a given body. Yes, I'm done.
teacher, what's the difference between the velocity and acceleration? I know the acceleration equal v over t, but all v and v have like force or velocity, But what's the difference?
Okay, the difference is this. Velocity is the rate of change of distance or displacement. Okay, velocity v. Gosh. Velocity v is the rate of change of displacement with time, dv dt. Okay, displacement is the distance, but with a specific direction. Okay, a body moves from point A to point 2. Okay, moves in this direction. It has been displaced. So the rate of change of the displacement with time is the velocity, and the magnitude of the velocity is speed. Speed, like more or less how fast something is moving. Okay, that is the practical meaning. Now, acceleration, as you are moving with a given velocity, velocity changes with time. Let's say you have your car, the speedometer. Let's say you are traveling at 80 kilometers per hour, and then you want to go to the mall. The speed limit is what? To the mall, I think it's 120 kilometers per hour, isn't it? But here in Africa, within the town, maximum you have is 80, isn't it? So you would like to increase the speed from 80 to 120, isn't it? Do you understand? So when you change the speed, that is accelerating. When the speed changes, let's say from 80 to let's say 120, you are now accelerating, which is now the rate of change of the speed with time, dv dt now, which is now acceleration. Whenever you have change in the magnitude of the velocity or change in the direction, sometimes the magnitude may remain the same, but the direction changes, then you are accelerating. Do you understand? And Hamdan?
Yes, teacher, I do.
Okay, so this is the difference between velocity and acceleration. Okay? While velocity is the rate of change of distance, displacement with time. Okay? So this is now the inertial force, which is equal to, the rate of change of momentum. Okay? Let me clean this. discard.
I think teacher second law is important when we have before we graduate an interview and some tests. Sure, ask us about the second law.
No, you need to know all the laws. I tell you this. Last week and 2 weeks back, we have been conducting interviews. In every interview, I tell you, I ask the candidate to tell me either the first law, second law, or the third law. And these are PhDs. They did their BS, MS, and PhDs. You understand? But yet, they have to be able to explain these laws clearly. Yeah, I'm in class. The one from Jordan. When we had sorry for the distraction. My chairman was knocking on the door. So, right. So, each I have to ask them this because it forms the basis of civil engineering analysis. You cannot forget them. Do you understand? Now, on the inertial force, we see F equal m, and acceleration is simply the change in velocity or change in time, okay? Which is, and this is momentum. Mass times velocity is momentum. So this is like the rate of change of momentum, okay? So the inertial force can simply be represented, and remember, mass is what? Times volume, isn't it? Volume, density times volume, okay? V dt. So we can simplify this, the density, the volume, if we are considering cubed, okay, this will be proportional to this. This is the velocity and characteristic time, okay? L over T is also another velocity. So this is also proportional to rho L squared V squared, because V is equal to L over T. So if we remove one L here, it becomes L squared. So L over T is V. So we have, instead of one V here, we have two. Okay. And remember, what did we have for the Reynolds? For the we simplified the viscous force. This is the simplification of the inertial force, isn't it? The viscous force was simplified to be mu. Is it LV? Isn't it? Right. So when you have now the Reynolds number, which is the ratio of the inertia, the ratio of the inertial force, which is rho L squared V squared, the viscous force, mu LV. Okay, so this cancel out, this one cancel, and then you have rho L V over mu. And this is the same thing as VL over mu, because mu over rho is equal to mu. And this is what this is the characteristic length, okay, which for pipe we use D, okay, for pipe flow. For open channel flow, we use R, okay. So you can have the representation of Reynolds number. This is for open channel flow. For pipe flow, we use VD over mu, where D is the diameter in this case. You understand? So this is the simple addition of the Reynolds number. Do you understand? Now let's move on to we define the Reynolds number as the ratio of the inertial force to the viscous force. So if the viscous force is so much, meaning when the viscous force the forces are dominating, it results in the Reynolds number to be low, isn't it? Because this is the viscous force. If it is high, then overall it will make the Reynolds number, if this is high, then it makes the Reynolds number to be small. Okay, and that is why for smaller, for laminar flow, the viscous forces are dominating, you have Reynolds number to be less than 500. For open channel flow, for pipe flow, it's equivalent to 2000. okay, less than 2,000. For open channel flow, it's less than 500. And this indicates that you have viscous forces are dominating the flow. If you remember, when deriving equations, we normally neglect the viscous forces, okay? We neglect the effect of the viscous forces, most especially if we are far away from the boundary, because the viscous forces are more significant on the fluid particles close to the boundary, okay? And for open channel flow, you have the velocity profile like this, okay? If this is the channel bottom, so they are impacting up to this height, which is the boundary layer region. And then when you go above it, the impact reduces, okay? The impact of the viscous forces, of the shear stresses acting on the bottom, okay? The impact on the fluid particles, it reduces. So that is why more often than not, we neglect the effect of the viscous forces, okay? But neglecting them does not mean they don't exist. They exist and they affect our flow. But for simplification, we normally neglect them. So when you have viscous force dominating, you have Reynolds number low. For turbulent flow, you have the viscous forces to be weak because the velocity is very high. And look at the formula, BR over more. So the velocity is very high. So it will overcome the effect of the viscous forces. So for that, the Reynolds number is high, greater than 2,000. Turbulent flow. Okay, in this case, the viscous forces are weak, or they have been overcome because of the high velocity. Okay? And between 500 to 2,000, you have what is called the transitional range. Okay, it is neither turbulent nor laminar. It is the transition from laminar to turbulent flow. For laminar flow, you have well-structured streamlines. The streamlines are clear, could be parallel depending on uniform flow also. Okay, but you have well-ordered type of flow. But the velocity is also very low. Once the velocity increases, then it will take the form of turbulent flow. But I told you most of high flow and open channel flow are turbulent flow. Okay. And if you remember in our previous experiments that we did in the lab, we have simulated when you have well-ordered type of flow, and then once you increase the discharge, the velocity increases, and then you have like some turbulent flow. Okay, so experiments on smooth channels and rough channels indicate that the Darcy-Weisbach formula of flow in pipes, which is equation 15.2, is applicable to uniform flow in open channels. This is the Darcy-Weisbach equation. Okay, it gives the head loss due to frictional head loss. Okay, as we are going to see in the next chapter, we have different head losses that is occurring whenever fluid is flowing. But the most significant and important one is the frictional head loss. You have head loss whenever you have change in direction of the fluid flow. You have head loss whenever you have reduction in the flow area. Okay, you have head loss due to a lot of other things, but these are termed as minor head losses. You have minor head losses and major head losses. The major head loss is the frictional head loss, which is as a result of the friction between the fluid and the boundary surface. Okay, and this is estimated, the frictional head loss is estimated using this formula, using the Darcy-Weisbach formula. F L over D, V squared over 2G. F is called the friction factor. L is the length, D diameter, okay. V is the velocity. This we will use, in the pipe flow. Now, still on the state of flow, now we use the Reynolds number to classify flow into, laminar and turbulent, okay. Now we will use another dimensionless number, which is called Froude number. Froude is the name of the scientist that worked so well in that area. Okay, so here it says the gravity effect is incorporated in the Froude number. The Reynolds number incorporates what? The viscosity effect, the viscous force. Okay, inertial force to viscous force. Now, when we take the ratio of the inertial force to the gravity force, the gravity force is simply the weight. That's the gravity force. Okay, it's simply the weight. So the Froude number is represented by a ratio of inertial force to gravity force now, okay, which is simplified as Fr equal V divided by square root of GD. V is the velocity, and D is the in this case for it's going to be the hydraulic depth, which is A over T. Okay, which is A over T. This case is the hydraulic depth. Okay, in pipe flow it will be the diameter. Now, fluid number has very important. Has very important role to play in the characterization of flow. When fluid number equals 1, the flow is in a critical state. Okay, we call the state critical. Okay, when it is less than 1, we call the state of flow to be subcritical or tranquil, having low velocity. Because you can see also fluid number is a function of velocity. Okay, it depends on all others. Like G is constant, hydraulic depth is the area over the top width, okay, which is also constant for prismatic channels. So basically, GD will be constant. So it varies with the velocity, okay. If the velocity is low, it will give low fluid number that will be less than 1. And we call the state of flow subcritical. This we will analyze practically in the lab, okay? And when it is greater than 1, the state of flow is called supercritical flow or shooting. It has high velocity, okay? It has high velocity. Is it clear? So you can see, so critical flow, for critical state, the velocity will lie, the velocity in critical state will be greater than the velocity in the subcritical state, but will be less than velocity in the supercritical state, isn't it? So when V equal 1, this is when the fluid number equal 1. This is when it is less than 1. Okay, less than 1. This is when it is greater than 1. So it is a function of velocity. Like I said, we will observe all these in the lab. Okay, one of the experiments that we are going to do today, even today. Yeah, we will start today, because today what we are going to do in the lab is we are going to measure the fluid velocity. Okay, the flow velocity using the pitot tube. Okay, so we are going to be measuring the velocity, and we'll measure the velocity at 3 regions: the critical region, subcritical region, and supercritical region. Now, how did we arrive at what is the derivation of the fluid number being equal to this? Okay, how do we derive it? I just finished the derivation for the Reynolds number. Okay, so for the fluid number, it's also like similar. Okay, because the fluid number is the ratio of inertial force to the gravity force, and we simplify the inertial force to be L rho L square V square. Okay, the inertial force. Then now the gravity force is also simple. The gravity force is the weight mg. Okay, and m is rho v. Okay, and then g. So v, if we use the characteristic, it will be proportional to L cube. Okay, if we have a cube. Okay, g. And that's it. So the fluid number now is now going to be the inertial force rho L square V square over rho L cube G. Okay, and this cancels out, this cancels, so you have V squared over L G. Okay, we have V squared over L G. Okay, and then since it is a non-dimensionless number, when we now take the square root, we now have V over root GL. L is the characteristic length, which is equal to D for open channel flow, hydrology for open channel flow, and it's equal to the pipe diameter. Okay, and it's equal to the pipe diameter for pipe flow. Okay, so this is simply the derivation. The rate of change of momentum is equal to, when you sum the forces, remember, sum of all the forces acting is equal to the mass times the acceleration, isn't it? So what are the forces acting on our fluid element? We have the viscous force due to viscosity, and the shear stress acting, and we have gravity force due to the weight, and any other force that we can think of. Again, all these forces, when added, is equal to the rate of change of momentum, which is equal to ma. Okay, now how about when we divide throughout by the rate of change of momentum? Okay, this becomes 1. Okay, and we have viscous force over rate of change of momentum, gravity force over rate of change of momentum. Okay, and then the rate of change of momentum is what we simplified as the inertial force. Okay, which is this. Okay, rate of change of momentum is simply inertial force, which is given by ma. Okay, so now this is like the inverse of the Reynolds number. This is like 1 over Reynolds number. Gravity force to the inertial force, this is like the inverse of the fluid number. Okay, and then this gives finally the fluid number. Okay, let me just look at what you are writing. Okay, so force as an object equals A equal B over T, velocity is high. Yeah, it is in between subcritical. The velocity in the critical region is in between, is greater than the velocity in the subcritical region, but less than the velocity in the supercritical. So it's like in between the two velocities. Okay. So let me go back to the presentation. Right. This is about 50 minutes since we started the lecture. So let's take a few minutes break, about 5 minutes, and then come back to continue on the critical flow condition, okay, where we will derive the specific energy. Yes, gentlemen, we're back. Let's continue. So now analyze the critical flow condition. Okay. And here we'll introduce the concept of specific energy. Remember the Bernoulli. Yes.
Will you update this chapter?
What?
Will you update this chapter, teacher?
Will I update what?
This chapter, chapter 14.
Yeah. After the lecture, I'll upload the updated presentation.
Yeah, because when I check the Blackboard, it's here. We have chapter 14.
What?
I
What?
mean, chapter 14 on the Blackboard, you know?
It's not there?
No, it's here. But will you do
Yeah,
some
don't worry.
updates?
I updated it, so that's why it will be slightly different from what you have. So I will upload the updated version after the class.
Okay, thank you for your efforts, teacher.
You're welcome. So remember the Bernoulli's equation, okay? Or the energy equation. You have Z plus Y, plus V squared over 2G to be equal to a constant, which is the Bernoulli's equation, or Z1 V1. Okay. So now Z is the datum. Okay, is the elevation above datum. Okay. And if we set Z to be 0, what we'll be left with? We have the specific energy, because each of these terms, this is the head expression. Okay, you have the pressure expression as well. Okay, because they are although they are like in form of head or depth, okay, but they are simply the energy per unit volume. Okay, the initial one, you have like, this is the velocity head, which takes care of the kinetic energy. Okay, kinetic energy. This one, okay, takes care of the what is called the flow energy. Okay, and this one, due to the elevation, takes care of the potential energy, PE. Okay, so it's simply the energy per unit volume. Okay, energy per unit volume. Okay, when you have pressure, let's say rho GH. Okay, potential energy is mgh, isn't it? It's mgh. So now m is what? Mass. M is mass, which is given by the density times volume, gh. Okay, so pressure is simply now, when you are substituting this back here, it's simply the potential energy per unit volume. Okay, and each of these terms, can be expressed either in form of a pressure head, or pressure or head. Okay, so pressure force is simply force over area, or the potential energy per unit volume of the moving fluid. So now when we set the datum to be 0, okay, Z equals 0, what we'll be left with is what is called the specific energy. So that's why I took my time to elaborate why the word energy. Okay, because ordinarily, in the Bernoulli equation, it's also called, you have the energy equation. Okay, So we call it specific energy when Z is 0. And it's simply equal to the depth of water Y plus the velocity head, V squared over 2G. Okay. And here when we substitute QA equal V, we have this, which we can plot. The first term on the right is relates to the static energy head. Okay. The static energy head, which is the first term on the right, which is as a result of the depth. Okay. As a result of the depth due to the static energy head. Remember, pressure is mgh. Okay, mgh. And so when you express it in terms of the head, okay, this is y now. Okay, what is the static energy head? Now, and the second one is the kinetic energy, okay, which I explained, okay, is the kinetic energy. These have been plotted separately and then combined in figure 11.2 for a graph of the depth against the specific energy. For a constant discharge, here we kept the discharge to be constant. What do we have? We have this specific energy. This is the depth. Remember, specific energy is simply y plus b squared over 2g. Okay, and this is the depth. Okay, so when you plot, you can see this is E equal the static energy. You know, we broke it into two, the static energy and the kinetic energy. So this is the static energy component and this is the kinetic energy component. So we plotted them separately. Y versus Y will be linear, isn't it? Y versus Y will give us this, which is the static energy. Okay, energy due to height of the fluid. Okay, and then the kinetic energy, which is V squared over 2G, which is this. Okay, when plotted against Y will give us this. Now, combine this 1 and 2, the formula of the specific energy. When we sum them up, we get the third one, which is this one. Okay, so this is the actual plot of the specific energy, which is Y equal V squared over 2G. Okay, so now at this point, you see, you can see at this point the depth, you know, when the specific energy increases, okay, it comes to a point where you have like single point. But for all other points, for the specific energy, you have two depths. Okay, for single specific energy value, you have two different depths. For single value of the specific energy, you have two different depths. Okay, and these depths are what? The subcritical depth and the supercritical depth. Okay, the subcritical depth, which is Y1. This is the supercritical depth, which is Y2. And this is the critical depth, which is YC. Okay, you can see it here, which is YC, the critical depth. Okay, and the critical depth is recorded here at this specific energy value when you have only single value. When you move away, you have depths on both sides. Subcritical, supercritical. So this is the supercritical region, and this is the subcritical region. The subcritical region, the velocity is low, V is low, isn't it? In the supercritical region, V is high. In the critical region, V is lying between subcritical and supercritical. Okay? So this is just the simple explanation. And here, the condition of a minimum specific energy, dE dy, equals 0 for a constant Q. Here, when you differentiate at this point, the slope gives you 0. Okay, dE dy. Okay, don't forget this is E and this is Y. Okay, so the slope here gives you 0, dE dy, because In this case, when you look at it, it is parallel to the y-axis. Okay, it is parallel to the y-axis. So if you take the slope of this line, if you take the slope of this line, even though y may change, but e is the same. Okay, the e is equal to 0 because it doesn't change. Okay, so that is why dy is not equal to 0. Because when you take the slope, like I said, you will have y1 and y2. Okay, so but because the numerator is 0, 0 over dy will definitely be equal to 0. Okay, so that is the point where you have the minimum specific energy. Okay, you remember maxima and minima in application of calculus, probably math 1 or 2. Okay, so dE dy equals 0. Okay, and when you differentiate this with respect to y for constant q, okay, for constant q, dE dy, use it this way. Okay, q squared. Okay, dA dy, because a is a function of the depth. Okay, and dA dy is simply the top width. Okay, the top width. You remember dA dy, and a over t is equal to the hydraulic depth. Okay, a over t is equal to the hydraulic depth. So what are we doing here? This dA dy is being replaced with t. Simple. So what do we have? We have 1. Why is it not? Okay. You choose. Okay. We have 1 minus 2q squared, or 2a cubed times t. Okay. But a over t is equal to d. A over t is equal to d. So this we will have what? 1 minus 2q squared over 2g a squared now, because 1a is out. Okay, and this is now d. Okay, and this is equal to 0. So when you now move this other side, you have it so to cancel out. Okay, and then you have v squared equal v squared over gd equals 1, which when you square both sides, you have v over gd equals 1. Okay, which is what? This is the fluid number. Remember, this is the fluid number. So meaning at this point, at critical flow, at this point, at this point, dE dy equals 0, and fluid number is equal to 1, isn't it? Because when we go and differentiate this equation with respect to y and equate it to 0, we realize that V is over square root of GD is equal to 1, okay, which is the fluid number, which is representing the critical flow state. So that is why, if you remember, we mentioned that for critical flow, the fluid number is equal to 1. And then for critical flow, it is less than 1. And for supercritical flow, it is what? Higher than 1. Okay, for supercritical flow, it is higher than 1. And here, normally, you have the velocity of flow to be higher when you have lower depth. Okay, so here, this region, this is the subcritical region, and this is the supercritical region, and the flow depth is low. Okay, so this will actually be substituted here. Okay, this is the supercritical region, and this is the this is the supercritical region where the velocity is high, and this is the subcritical region where the velocity is low. Okay, where the velocity is low. I told you all this. We are going to do it today. I mean, it's part of what we will examine. Okay, we will examine the supercritical region, subcritical region, and the critical region. So the fluid number is equal to 1. Okay, and this is the condition for critical flow. Even last week, I asked someone, I interviewed him. I asked him, what is the value of the Reynolds number? And I asked him again, for subcritical flow, what is the value of the Reynolds number? And for supercritical flow, what is the value of the Reynolds number? I'm not supposed to forget these things. They are the basics. I always tell you this. Okay, like Reynolds number for laminar flow in case of pipe and open channel flow. You are supposed to not like memorize, but you are supposed to know them. Yeah? It's like G equal 9.81. You need someone, or the density of water equal 1,000. Do you need someone to tell you that density of water is 1,000 kilogram per meter cube? You are supposed to like remember this all the time. The same thing with, let's say, the Reynolds number for laminar and turbulent flow, open channel and pipe, and the fluid number, for critical, subcritical, and supercritical. Then we'll move to the next part, which is the computation of critical flow. Okay, computation of critical flow. Now, from this equation, when deriving this, from this, we can take this one, okay, by transferring Q A to the other side and D, okay, and then squaring both sides, okay. How do we do it? Let me just simply do it here. You have A squared, simplifying from here, okay, A squared D be equal to Q squared over G. Okay, so here you can take the square root of both sides. Okay, so that will now give you A root of D be equal to Q over square root of G. Okay, but remember at the beginning we called this A root of D into square root section factor for critical flow, ZC. Okay, so ZC is equal to now Q over square root of G. We use critical flow for the design, okay, for the design of open channel flow, okay. We use this section factor for critical flow, okay, which is derived when the specific energy is minimal, okay. And when it is minimum, you have critical flow taking place, okay. We are going to see next week how we will utilize the section factor for critical flow ZC in the design of channel design. Now we'll look at some computation of the critical flow. Okay, so in the figure, porphyry is almost vertical at the critical depth. Okay, a slight change in energy can cause substantial variation in depth. A slight change in energy, that is here. When the energy changes slightly, it can cause substantial variation in depth, either in the subcritical or supercritical region. Okay? And the flow at the critical state is thus unstable, and the water surface appears wavy, wavy, something like this. The water surface like a wave, okay? Because it is so unstable, because a slight change in the energy can cause substantial variation in the depth, okay? So in terms of channel design, if the depth is determined to be at or near the critical state for a great length of the channel, the shape or slope of the channel should be altered. Why should it be altered? Because the critical state is unstable. Okay, it should be altered such that we don't have the critical flow for a great length of the channel. Okay, and critical flow, however, serves the purpose of a controlled section. It is useful in defining flow conditions and developing surface profiles. Okay, we didn't discuss about the surface water profiles. This will be probably for those that may want to take the water conveyance course. Okay, I will be discussing the surface water profiles depending on the type of flow, gradually varied flow, rapidly varied flow, and then we'll discuss what is the surface water profiles. So it serves as for good purpose of a control section, okay, defining flow conditions and developing surface water profiles. The slope of a channel at which computed uniform or normal depth of flow is equal to the critical depth is known as the critical slope. What are we saying? When the computed uniform depth or normal depth of flow is equal to the critical depth, is known as critical slope. Depth here YC. So when Yn, which is the depth of flow for normal or uniform flow, which is equal to YC. So the slope when this occurs is known as critical slope, SC. Okay? It's known as critical slope, SC. And a slope less than the critical slope, this we are explaining how, we'll be talking about the development of the surface water profiles. The slope less than the critical slope is the mild course of critical slope, and the slope greater than the critical slope is the steep or supercritical slope. These are important in flow profiles. Let's say you have a critical slope with this. Let's see, which is the critical slope. Okay. The slope less than the critical slope is mild slope. Let's say this one. See, this is less than mild slope. In this case, definitely you can see the velocity will be less than the velocity here because this is steeper. What about the slope greater than the critical slope? S or steep slope or supercritical slope. Okay. When water is flowing here, definitely the velocity here would be greater than the velocity in the critical state. And the velocity in the critical state is greater than the velocity in the mild slope. Okay. So we use these slopes in the description of the surface water profiles as well, because the bed slope also affects the characteristics of the flow as well as the surface water profiles. Okay, but we will not go into in depth into this. Okay. Now let's take an example here. A rectangular channel is 25 feet wide and has a flow of 500 cubic feet per second at a velocity of 5 feet per second. Okay, so this rectangular channel and the width is 25 feet. Okay. A, determine the specific energy of water in the channel, and B, what is the critical depth of water in the channel. C, what is the critical velocity? Because at critical depth, water has some velocity. So what is that velocity? So from the continuity equation, which is Q equal A, okay, this is the velocity already given. The flow rate, the velocity, and this is the width, this is B. Okay, so we can get the area. Okay, we can get the area. As once we get the area, we can get the depth of flow, which was not provided. We only have B. But what is the depth of flow? This is what we found to be 4 feet. Okay, now we just go to the specific energy, which is simply Y plus V squared over 2G. Y is already obtained from here. V is already provided here. And then we substitute. So this is the specific energy. Okay. And now the second part says what is the critical depth of water in the channel. Okay, so for critical depth, this is the section factor 2 over square root of G. Okay, so this is the section factor. And now find the critical depth. If YC is the critical depth, then for a rectangular channel, the area is BY, at YC now, okay? This is the area, and this is D, which is the hydraulic depth, A over T, okay? This is the area, and the top width is equal to B, because top width is here, which is also equal to B in this case for rectangular channel. But for trapezoidal channel, you will see that this B, the top width is not equal to, here the top width is not equal to B, it's greater than B. Here the top width is equal to B plus, we are going to see plus 2 into I into maybe square root of minus something. We are going to derive it because we need to know this, okay? We need to know this. So this is B plus these two sections, okay? We will derive it very soon. But for rectangular channel, the top width is equal to the the width, okay? So this is E, and this is, so here the hydraulic depth is equal to Y, okay? It's just equal to Y for rectangular channel, and Z, which is A square root of D, is now, we now substitute, okay? We computed Z here using this formula, but Z is also equal to A square root of D, okay? So we are now evaluating this in terms of Y, so that we can equate whatever we have with this value to obtain YC, okay? So that's exactly what we did here. This is AD, and this is equal to this one, and YC is the only thing unknown which we found, okay? You can see that the critical depth YC is less than the flow depth, which is 4. Flow depth is 4, but the critical depth is occurring at 2.32 feet, okay? Occurring at 2.32 feet. And what is the critical velocity? We use the Froude number, because at critical flow, the Froude number is equal to GD, okay, is equal to 1. Okay, so V is equal to root GD. And D is equal to YC. You can see that D is just equal to YC. Okay, so we use this now to get the critical velocity. Okay, and definitely you can see that the critical velocity is higher. Okay, so like I said, when you compare it now, the velocity, this is 5, the velocity, and the depth, Y is equal to 4. Now, for the critical velocity is equal to 8.6, and the depth is equal to 2.3. Okay, so when you analyze, you can see when the depth is higher, the velocity is lower. When the depth for critical flow, it reduces, the velocity becomes higher. Okay, velocity becomes higher. So the velocity is usually higher when you have the flow depth reducing. Okay, and that is why I told you here.
Teacher, this only in channel.
What? What?
This relationship only in open channel and rectangular.
What? Yeah, this is for open channel.
Okay.
Yeah. That is why I told you here that this
Yeah,
is.
I know, teacher, this in channel, but do we deal with this relationship in other shape or only in channel?
What?
I mean this relationship between velocity and y.
Relationship between velocity and Y?
Yes, this only on a channel, or can we deal with other shape?
I still don't understand your question clearly.
I mean, teacher, when we have y high and velocity is reduced. This only only on channel, or can we deal with other shape?
Or can you deal with other shapes? Yeah, even with other shapes, as long as it is open channel.
Yeah, other in other channels, can we deal with a rectangular and circular, or just
No,
only on channel?
no, you have the same thing. You have the same thing. Okay, as long as it is open channel. Okay. So that is why I told you here. You can see here the depth is lower. So this is the supercritical region. And this is the subcritical state. Okay. Because the depth here is higher and it is lower in this case. The velocity is higher when you have the depth to be lower. Okay. The velocity is higher. And this, like I said, we are going to observe in the lab today. Okay. And right, so this is the velocity for critical flow. Now, this is another example. The first one we had simple rectangular channel. Now we have trapezoidal. Right. You have a trapezoidal channel here with a bottom width of 4. This is the bottom width, 4 meters, and side slopes 1 to 4. This is a side slope. The side slope will help you find this. Okay. Will help you find this. Okay. 1 to 4 carries a discharge of 30 meter cube per second. Determine the critical depth, critical velocity, and minimum specific energy. Okay, minimum specific energy. So the first thing it says to determine the critical depth. Okay, the critical depth will be YC. Okay, but to determine YC, we need to find the top width. Like I said, for trapezoidal channel, this is B, and this is also B. But we need to know these other sides. Okay, it has the same side slope. Some may have different side slope. This is 1 to 4, 1 to 4. Okay, so we use similar triangle here. This is Y. If I call this X, okay, so it means, you know, Y over, or X over Y, X over Y is equal to 4 over 1. 4 over 1. So that means X is equal to 4Y. Okay, so X here, this is 4Y, and this is also 4Y. That's why you have 4 plus 8Y, which is the top width. This is now the top width. It's a simple geometric, analysis here. So, the section factor is Q equal over square root of G. This chart has been given, so this is the section factor. Of course, it is also equal to A square root of D. So that is, now we will now express A and D in terms of Y, D. And then we equate it to this one to get our YC, just similar to what we did before. So now the area, this trapezium, not rectangle, area of a trapezium is half sum times sum of the parallel sides times height. These are the parallel sides, B and the top width. Okay, so the area of the parallelogram is half times sum of the parallel sides. In this case is B plus T times height, and the height in this case is going to be Y. Okay, so B is 4, T is 4 plus 8Y, and then y is y. Okay, so this is A. Okay, and D. So A equal A into square root of D. So this is A into D is A over T. Okay, which is simply because this is A, this is A. So you have 3 over 2, the power of 3 over 2. Okay, so we substitute A and T here. So we now have this to be equal to this amount, 9.58. Okay, now using this formula, ZC is computed for various selected values of Y. You can see you cannot easily solve for Y here. Okay, it's not like Y equal 2y equal x, y equal x over 2. Okay, so here ZC is computed for various selected values of y in table 11.3. Okay, meaning y values have been varied, and then ZC is computed, and a plot is done of y versus ZC. Okay, and then ZC corresponding to this value has been obtained. Okay, wait, let me. This is the, so y was varied. Okay, so 1, 1.5, 2, 2.5, and then ZC was calculated. Okay, ZC was calculated, and then it was plotted. Y versus ZC. Okay, Y versus ZC was plotted. Okay, and when it was plotted, you remember we determined ZC before. ZC was initially determined using the first formula, Q over root G, which is 9.8, 9.58. Okay, so we now go to that plot to get what is the depth, because we now plot Y versus ZC. Okay, so we now, what will be Y if ZC equals 9.58? Okay, and the value of Y will give us the critical depth, and that's it. So 9.58, YC equals 1.22 meters. This is because, you know, you can, there is a way you can find Y from this, okay, using what is called trial and error method. Trial and error method. How do you do? You put this value, let's say, in a calculator, and try to be varying, changing the variable Y, okay, to see will it give you, how close will it give you 9.58? Okay, if you substitute Y equal 2.12, sorry, 1.22, it will give you almost exactly to be equal to 9.58. So this is like another way of dealing with such problems, because sometimes in flow problems like this, you will end up having such equations in which you will have to use either to plot, which takes time, or to use the trial and error method. In the trial and error method, you know, you keep on like changing values, and then to see how close is it to this one. Okay, then the value that gives you closest to it, you know, that gives you the value of the unknown variable. So that is the critical depth. The second part of the question is the critical velocity. Okay, the critical velocity, which is simply square root of GD. Okay, and since we know the critical depth, we can substitute, because the hydraulic depth is A over T. Okay, so we can substitute the critical depth now to find the hydraulic depth, and put it back here to get the critical velocity, which is 2.78 meter per second. And the specific energy at critical state, simply apply this formula and add it up, and this is the specific energy. Very straightforward. So the most important thing in this case is finding the critical depth, because the critical velocity depends on the critical depth, and as well as the specific energy. Okay. Now, That is for critical flow. What about now uniform flow? Okay, or uniform channel flow. For uniform flow, it occurs in steady state only. This we explained before. Because it is when the flow variables do not change with space, okay, with position. So they do not change with position, okay. Uniform flow occurs in a steady state only. And you know steady state, that is that the flow variables do not change with time also. Okay, so if it doesn't change with position, then it has to be constant in time as well. Because like when moving from this to this point, a flow field, okay, it takes some time to flow. So if the variables remain the same, then it has to be a steady state as well. Okay, so uniform flow occurs in a steady state only. And whenever you have a uniform flow, then the flow is uniform as well as steady. The uniform flow, the depth, area of cross section, velocity of flow, and the discharge at the same, and the discharge are the same at every section of a channel. Okay, they are the same at every section of a channel. And such a condition develops when the force in the direction of the flow is fully balanced by the resistance encountered by the water as it moves downstream. This does not occur frequently. Okay, when you have the force, force in the direction of the flow, which is like the inertial force, okay, is balanced by the resistance encountered by the water, okay, as it moves downstream. This does not usually occur. The resistance here, as it moves downstream, is in form of the viscous forces. Okay, long channels may have only small reaches of uniform flow. Okay, meaning small distances. Okay, small reach meaning small distance where the uniform flow can be said to occur. However, uniform flow is a basic flow in hydraulics. Okay, in channel hydraulics, uniform flow is a basic flow, and channel design are based on conservation of the uniform flow. Although uniform flow occurs in small reaches of the channel, channel designs are based on consideration of the uniform flow. Meaning, even those sections that uniform flow do not prevail, we assume that uniform flow is prevailing. This assumption is to simplify things, is to make life easier. Because when we assume uniform flow prevails, then steady flow also occurs. And that will make us drop many variables that may be varying with time, with distance, and all that. And it makes the analysis and the design simpler and easier. Okay? Of course, there could be a lot of other things to be considered, to ensure that the design is really realistic. For most designs, we try to make it as simple as possible, because if it is not uniform flow, even the velocity, you need to have a lot of other variables that may not be there, that will make your equations highly unlinear. Okay? So hydraulics of uniform flow. The common approach in the United States is to use the Chazy-Omanin formula. My time is up, so I'll stop here. Next week we will continue from here, and from here we'll move to the design of, the channel design. Okay, to the channel design. Any question?
Teacher,
Yes.
our major from where to where, teacher?
What?
Our major from where to where? What's selected?
Major? Yeah, it will critical flow. So just
I can't hear.
uniform, yeah, up to critical flow computation. Okay.
I can't hear you, teacher. Again, please.
The major will be up to flow computation, up to the computation of the critical flow.
Oh, so from chapter 5 to 14.2.
Yeah, let me check.
Can we drop teacher
I
chapter
don't know.
14? I think from 5 to 13 is good.
Yeah?
I think from chapter 5 to 13 is better than
No, it
14.
will be. Okay, I will check. I will check as far as the schedule. Wait. Let me just open the schedule to see what we have. Yeah, so major 1, okay, 4 chapters, chapter 1 to 4, right? And then major 2, 4 to 7. Oh, okay. Theory. Uh, 2, 4 to 7. But so I think, okay, don't worry, I will check it. It will not include 14, don't worry. Okay?
So from 5 to 13.
No, not, it will not include 13. All indications, okay? Okay? So don't worry, I will check.
So we will discuss this in lab, okay?
Yes, all right.
Okay, see you teacher.
Okay, see you.